Hello, my name is Jan-Malte Giannikos, and today I will present my project on haptic grasp quality prediction with natural language context, which was conducted during my 2023 RIS internship. Motivation. Grasping is a commonly needed task within the space of robotic manipulation. Most current approaches rely on computer vision, either partially or completely. While this approach generally yields good results, visual data is not always readily available. Occlusion or bad lighting conditions, for example, can heavily restrict visibility and challenge these methods. Instead of relying on vision, we use haptic sensor data as an alternative sense we can equip our robot with and combine it with context knowledge. This context knowledge is extracted from natural language prompts, which might be provided by human cooperators or instructors. Datasets. Dataset generation in simulation. To train our model, we generate a large dataset of grasp interactions in simulation. We use PyBullet to simulate physics and Tacto to generate the simulated haptic sensor outputs. The haptic sensor outputs can be seen on the right together with the robot configuration that produced the displayed feedback. The RGB image is the raw sensor data we actually use in our model, while the black and white images show a depth map. Grasp interactions are generated by choosing a random grasp point that lies within the object and a random gripper rotation around the global z-axis, before grasping from the top down. If the gripper collides with an object before it can reach its final destination, the movement is aborted and a grasp is instead performed at the current location. After a grasp has been performed, we attempt to lift the object. If the object is lifted, we classify the interaction as successful. If the lift fails, we classify the interaction as unsuccessful. We use this sequence to generate a training set of roughly 50,000 data points spread over 5 different object types. Additionally, we generate a test dataset containing 1,000 data points per object for a total of 5,000 data points. Dataset generation in the real world. To examine how our model transfers to the real world, we generated a small dataset of 240 grasp interactions with 2 objects that had proven most difficult to classify in simulation. The procedure for generating our grasp interactions was generally the same as for the simulated dataset, with the key difference being that the grasp position was not chosen to be a point within the object geometry, but by randomly diverting from a base grasp position. We use a counterweight mechanism attached to the object to reset its position after every grasp, guaranteeing that it remained in the expected spot throughout the data collection process. Language dataset. In addition to the 2 datasets containing haptic sensor data, we generated a dataset containing 62 natural language prompts describing the objects being grasped. Each object has roughly the same amount of descriptions. However, some descriptions that fit more than one of the object shapes were duplicated. All language prompts were generated by hand. Model. Haptic convolutional neural network. To extract our haptic features from 2 RGB sensor readings, we use a convolutional neural network with 3 convolutional layers, each of which is followed by a max pooling layer. Finally, we apply adaptive average pooling before flattening our feature vector, which is then processed by the grasp quality classifier described later. Each layer uses ReLU as a nonlinear activation function, and we apply 2D batch normalization during training. NLP classifier. We use the large language model CLIP in conjunction with 3 fully connected layers to extract a 5-dimensional feature vector representing the 5 possible object classes from natural language prompts. This submodule is pre-trained to classify what object type a given prompt belongs to before being integrated into the larger model. During this training, we use dropout for regularization and cross-entropy as a loss function. Grasp quality classifier. The grasp quality classifier takes haptic and NLP embeddings and predicts if the given grasp will be successful. It consists of 2 fully connected layers and a softmax activation function. We train the entire model end-to-end and utilize 1D batch normalization as our regularization technique. We also introduce a baseline model which does not receive NLP embeddings but is otherwise equivalent to our model. Results. Performance on simulated dataset. After training both our model and the baseline for 20 epochs on our training dataset, we can see that providing NLP context does not significantly improve our performance, which is measured by F1 score. This is likely due to the fact that the dataset contains only primitive objects for which global information beyond local tactile feedback is largely irrelevant. Comparing the performance of our baseline on the default mixed dataset with a collection of baselines trained and evaluated on datasets containing only a single object each shows that the mixed dataset baseline is only marginally worse than the average of the object-specific baselines. This confirms that knowledge of the object type, which the object-specific baselines have implicitly, does not significantly increase the performance on the mixed dataset, making NLP context largely unnecessary. Performance on the real dataset. We fine-tune our model and the baseline on the real-world dataset and use a 5-fold cross-validation scheme to evaluate performance in order to show that our model can generalize to the real world. After 50 epochs of fine-tuning, we achieve a very strong performance both on the baseline and our classifier, with the baseline beating our classifier. This is likely due to the fact that our NLP module is built to work with 5 object classes and was not adapted for this dataset, which contains only 2. Additionally, the decrease in object variety likely made context knowledge even less useful. The experiment demonstrates real-world viability of the general model, while also highlighting some of the issues with the NLP embeddings. Future work. Due to the limitations of our dataset, our experiments failed to give conclusive evidence as to the feasibility of NLP context in haptic grasping. In future work, we aim to extend the dataset to more complex objects to rectify this issue. Additionally, we plan to explore how NLP context and haptic sensing could be interwoven to perform other, more complex manipulation tasks like autonomous grasping. Lastly, and most immediately, we plan on expanding the real-world dataset to allow us to more fully train and test on it. Acknowledgements. I want to thank Rachel Burson and John M. Dolan, as well as all others involved in organizing the RISH program, for giving me this opportunity to work on this project. Additionally, I want to thank Oliver Cromer, David Philip Lyons, and Alexandra Morningen for their work as my supervisors, and all members of the IAM lab for their welcoming attitude and generous support.